Welcome back to Differential Equations. In this video, I want to introduce you to Euler's method, which is the simplest approach for using numerical tools for solving a differential equation. By this point in the course, you should have come to two conclusions about differential equations. First of all, most of the time, when we can solve a differential equation, well, we can solve it in theory, but in practice, it tends to be incredibly difficult to actually achieve that solution. We've seen a number of places already where we've had, this is what a solution would look like, but we're missing that one piece of information. Or this is how you solve, but you have to evaluate this integral, and we don't know how to do that. The other thing that you should have noticed is that even when we're looking at that narrow window of differential equations we can solve, we've already eliminated many differential equations that in theory might be useful or interesting. Your experience in other mathematics courses probably leads you to assume that, well, I mentioned numerical methods, the computers are going to come to our rescue. You've seen that play out in countless other courses. Here's how to graph a line. Here's some computer software that will produce a graph of a function for you, and you don't have to worry about it anymore. Here's how to evaluate a definite integral. Here's how to write a computer program that will calculate the approximate value of a definite integral so you don't have to go through all that work by hand. And in a lot of those places, you learn techniques that are far superior to anything that you can do by hand. Unfortunately, differential equations is a little bit less susceptible to that than other tools. And in this video, I want to give you a little bit of a feel for what I mean when I claim that. So let me get my head out of the way, and let's turn our attention to a first-order initial value problem. Let's assume that we have a first-order differential equation that can be written in the form dy dt is some function of t and y. And then we have that y of t naught is equal to y naught. There's our initial condition. We've solved problems like this. We've seen sometimes they are separable, sometimes they can be solved using an integrating factor, and a couple of other tricks that have come up along the way. We also saw, if you go back to some of the first things we did with differential equations, that you can use the first order differential equation to generate a slope field. And then you can plug in that initial condition, you can follow the path along the slope field, and you can approximate what the graph of the solution is going to look like without solving it. And that's really what Euler's method is doing, although in a more pencil and paper style and less a click on the graph and see what the graph does. So our process for solution starts off picking a time interval that we're going to call delta t. And depending on the problem, this can vary greatly, but as a general rule, you generally want to have your model written in such a way that picking t or delta t is around 0.1 or 0.01 is probably the right place to be. And I just realized that I am switching up my order of my arguments. Let's go back earlier and change this to y and t, because that's the way the rest of my notes on this unit are written, and I'd like to maintain that. So we have some function of y and t. Notice up here that that function is the slope So if we take that slope, we evaluate it at our given point, and multiply by the size of our t-step, that will give us the size of our y-step. So all this stuff together, you can think of as delta y. So you take y0, you add delta y, you get y1. And then a lot more obviously, we'll find our next point t1 by taking t0 and adding delta t. It's the same thing either way. For t, it is a very clear way of taking the step. For y, it's a little bit less clear as we write it down, but it is still the same. And then we keep repeating that. In general, our y sub k plus 1 is y sub k plus f of yk and tk times delta t, and our tk plus 1 is tk plus delta t. And if you keep repeating that, you'll eventually get to the point Tn that is the point that you are interested in knowing about. And if you plot all of the points as you go, you can construct something that looks reasonably like the graph of the function. So there's the game plan. It's fairly straightforward, I like to think. Let's dive into an example. This is a fairly straightforward equation. dy dt is 2y minus 1, and y of 0 equals 1 is our initial condition. It's been a while since we've talked about this, but this is a separable differential equation. I can solve this whole thing analytically. If I rearrange it, it's dy over 2y minus 1 equals dt. I integrate both sides. And then I play around a little bit. I'm going to jump straight through all of the algebra just for the sake of time. But we've seen things like this. You should be familiar with it. We're going to raise e to the power. And then we're going to have to rearrange to solve for y, which means we have to add 1 and divide by 2. Then we plug in our initial condition, and it turns out when we plug in the initial condition, we find that a has to be equal to 1. So our particular solution is just that y of t equals e to the 2t plus 1 all over 2. Yay, we can solve this. And sometimes I think that's what makes the most interesting problems. We can solve this. We did solve this. But now let's look and see what it looks like to use Euler's method. Well, following Euler's method, y0 given in the initial condition is 1, and t0 is 0. And I actually want to put t0 over here to the left, so let's make room for that. t0 equals 0, y0 equals 1. Then we choose our time step. I had said before that if a delta t equals around 0.1, it is usually pretty convenient. And then that's going to give us that y1 is, we'll plug in t equals 0, y equals 1 into our right-hand side. We have 2 times 1 minus 1, which is 1, multiplied by delta t, which is 0.1. So it's 1 plus 1 times 0.1, which is 1.1. Then get our next time step. T2 is going to be 0.2. And y2 is going to be our y1, which is 1.1, times, plug in t equals 0.1 and y equals 1.1 to our right-hand side of the function. So 2 times 1.1 is 2.2, minus 1, which is 1.2. Multiply that by 0.1, and you get 1.22 as our result here. This is a numerical method. Numerical methods are fantastic for use on a computer. They weren't originally invented that way. Remember, Leonhard Euler, for whom this method is named, was long dead before computers were even imagined as something that could ever serve practical purpose. So definitely people were doing this by hand at one point, but we live in the modern age. I'd rather spend more time learning the theory and less time crunching numbers by hand. So instead of continuing to work on this pencil and paper, let's let the computer do the work. And Euler's method is straightforward enough that we can use something like a spreadsheet, and that will take care of all of the work for us. So you can see that I've already entered in my first row, my labels, t and y. Let's go ahead and align these to the other side so that everything lines up nicely and it's a little bit easier to see what's going on. I put in my initial conditions, t equals 0, y equals 1. Now in the next line, I need to enter in my next step. So if I can type, I hit equal sign, I select the line above, and then I add my delta t, which I'll hard code in as 0.1. In y, it's a little bit trickier, but I'll go ahead and first type my equal sign. I'll select that entry above. I'll hit plus, and then I have to, let's put in some parentheses here. It's going to be 2 times the y value that we already have, which is this same value that we just selected before, and then minus 1. Right? That's evaluating my function at that point. And then I have to multiply that times my delta t, which is 0.1. Enter, that gives me my next entry. Then the fun of working with spreadsheets. If I select this row and I click in the corner and drag down, it will copy this row over and over again every time using the previous entry as my starting point. All right, so let's get a couple of values put in here. And I want to keep going until I get to around t equals 3. That's around t equals 3. All right. So we have y values going along with all of these entries for t. And in a lot of situations, that's it. That's the end of the story. We have solved our differential equation. We've gotten numerical values, and we can use those numerical values to do whatever it is we wanted to do with the solution in the first place. The particular problem that we are solving is interesting because we were able to solve it by hand. And so instead of just ending the story here, I want to look a little bit at how well the solution actually works. So I'm going to go ahead and select all of that data, and I'm going to copy it. Now I'm in Desmos, free graphing software. And one of the nice things about Desmos is that it will allow us to paste in data. So just Control V here, pastes in all of that data that I had just calculated. And if I get my head out of the way, we can see that it has graphed all of that data, and we have a nice look at the solution. I want to compare that to what we came up with. We have to put in x instead of t in order for Desmos to understand how to graph it, but the equation was y equals e raised to the 2x power plus 1 all over 2. And, well, that doesn't quite look the way that we hoped it would. And here we have our problem. If we zoomed in, and I'll do this in a minute, if I zoom in and just look at the region here, about from 0 to 1, our approximation and the graph are going to be in very close agreement. But as we continue onward, the agreement between the actual solution and our numerical approximation gets worse and worse. And that's just the nature of differential equations. Because every step, every point depends on the point that came before it, those little errors compound, and the further you get from your initial condition, the worse the situation is. There are some ways to get around that. There are some things that we can do to make our lives a little bit better, but it's not perfect. So, just like everywhere else in the study of differential equations, using numerical tools is something that you have to do very carefully. When the numerical approximation exists and is relevant and is stable in a way that the numerical tool wants to be able to solve that differential equation, you can go for it, you will get a good answer. If you use a numerical tool that is unstable with the particular type of differential equation that you're looking at, then you run into problems. Understanding numerical tools, understanding how to know when to use what, is a little bit beyond the scope of this course, but I wanted to make sure that at the very least you understood that there are numerical tools, they have their strengths and weaknesses, and you have to be a little bit careful with. All right, so what went wrong? There's a couple of different ways you can think about it, but the thing that I tended to think about is we started with the linear approximation. y1 is approximately equal to y0 plus f of y0 and t0 times delta t. But we've seen that you can expand this polynomial approximation. You could add the derivative, f prime, of y0 and t0 times delta t squared. When you do that, you're going to have to divide by 2 because it's the squared term. And you could continue with the next derivative. And you can keep going from there. Euler's method cuts off everything else. We call that a truncation error. And generally speaking, a truncation error is going to be very small, right? In our case, we chose delta t equals 0.1. Well, if that's the case, then delta t squared would be 0.01, and delta t cubed would be 0.001, and so on. So our delta t is small but important. Delta t squared is just hitting that it's small enough to not be noticed, and delta t cubed is small enough that we really don't have to worry about it even by comparison. But the important thing here is that if you take that whole term that has the delta t squared, Because the other terms are going to be even smaller, we can ignore those, and we can say that the truncation error is in the ballpark of that next term. If you have the tools that you can use to evaluate this, then you can start to figure things out. Looking at the particular initial value problem that you are trying to solve, you can figure out what this next term was going to be. If it is going to be large compared to your values, then Euler's method is going to be very bad for you. If this is going to be small compared to your regular values, then it's not really so much of a problem. Some of this really depends on your choice of delta t, but as we'll see in future videos, taking too small of a value of delta t introduces its own issues. It turns out that in a lot of cases there is noise in the data that can be amplified by using too small of a value. To wrap up, just to make sure that you understand what this expression is actually trying to say, I would like you to, using the problem that we've been solving in this video, figure out what the error is. What is the truncation error for the differential equation that we just tried to solve? See where you can get with that, and I'll see you in the next video.